Okay, we should be live. So welcome to the second day of the Summer School of the Assumptions of Physics.
And I think right now everybody who's joined has joined yesterday, so I think we don't need to go through long introductions again. I can quickly say I'm Christine Adela, professor of physics at the University of Michigan, and I co-lead the Assumptions of Physics project with Gabriele Carcassi, who's also in the physics department with me at the University of Michigan. And I think I will turn it over directly to you.
Very good. Okay, so let's just jump into it. Today we're going to talk about the second approach in a project of assumption physics, physical mathematics, and just to rehab a sort of high-level pictures. Let's go through the first couple of slides again. The main goal of the project is to identify a handful of physical starting points from which the basic law can be rigorously derived. And the issue that is going to be the theme of today is that you can't really do that without really rebuilding all the mathematical structures or even the most basic ones, because you can't expect your assumptions at a high level to be clear and fully define what you're doing if you're not doing the same thing for the low level. Like, you can't sprinkle meaning and correctness on top. You have to do it at the most fundamental layer and then grow the things consistently. And just to remind ourselves, the goal of the standard view in the foundations of physics is really that physics has to find the true law of the universe, the one that tells you how the universe works, what are the building blocks of the universe, and how they're put together so that you can get the correct ontology of the universe. You can solve all the problems that we have currently in philosophy and so on. And then there is this sense that that's the real physics and everything else is an approximation. And by working on this project, we have a different view because of the results that we've been getting. We are going to see today, for example, that assuming experimental verifiability, the requirement, the physical requirement, leads to the existence of topologies of single algebra. This to the requirement of topologies at sigma algebra at the mathematical level, that geometrical structure are equivalent to entropic structures, which are not typically seen as fundamental building blocks of the universe, that Hamiltonian evolution is equivalent to assuming a deterministic and reversible evolution or isolation, and independence of degrees of freedom. And isolation is always an assumption, is not something that you can do and take for granted that it's actually 100% true. And if you add this other assumption of kinematic equivalence, you recover massive particle and rotation forces. So the overall results that we are seeing is that the physical requirements and your assumptions that you put on the system that you're studying actually drive most of the theoretical apparatus. And so for us, it's a lot more productive to say that the goal of physics is to find models that can be tested experimentally, because then we start with models and an assumption of the model and derive a mathematical structure. While if we say that we are actually describing the true law of the universe, we wouldn't have a way to recover all the things that we need to recover, right? We would have to find a different way, and I have no idea even if you can do it. And this approach instead works, so let's continue with the approach that works. And so really what we want to set up, and we're going to see it a little bit more precisely in this series of lecture today, talking about physical mathematics, that we basically want to develop a theory of physical models in the same way that the foundation of math essentially describes what it means to do math, what is a proof, what is a set of axioms, what can you prove in a set of axioms, or the foundation of computer science, defines what is a computational machine, what is the models of computation that you have, what can you prove, what you cannot prove, what you can transmit, what you cannot transmit. We basically want to have the same feel as a foundation of physics. We want to say, what are the requirements of a physical model? What is a physical theory? What can you do? What you cannot do? What is the space of the possible physical theories? And so we want to have first a set of general physical principles and requirements that all physical theories must satisfy, because they all need to be experimentally connected to experimental verification. We need to be able to define systems, we need to be able to define states, we need to be able to define processes. And therefore, there are some basic requirements to be able to say, okay, I have a system that it's sort of separated from the environment. I'm doing some things. So there are choices that you have to make, and we need to be able to understand what those choices are. And then basically for those general principle requirements, you get a general mathematical framework, a set of definitions that are always valid in any theory. Right now, the notion of states in classical mechanics, in quantum mechanics, in thermodynamics is completely different. There is no like a most basic structure, right, that would satisfy all of them. You do everything differently. Instead, what we'd like to have is a sort of, if you're a software person, we want to have a super class than everything else that inherits, right? It's a little bit, as I said yesterday, it's like having the set theory of physics, and then everything is a set and everything inherits those basic properties. And then once we have something that it's in principle always valid, we can generalize the theorems that as much as we can in this general mathematical framework. And then we can take specific assumptions and find classical mechanics, quantum mechanics, thermodynamics, field theory, and possibly new theories as a particular instantiation of the most basic structure, plus additional requirement and plus additional features. So that's basically what we want to have at a high level. And as I said yesterday, there are two approaches that we have. The first is reverse physics, with the idea that we take the physical theories that we have that are described very mathematically, and we try to find a set of principles so that we can start thinking more about the physics than the math. And physical mathematics is exactly the opposite approach. We start from scratch. We start with the physical requirements and physical idea. We turn those in mathematical requirements, and then the mathematical requirements will give us a mathematical structure, and we can say that that mathematical structure is physical because it's justified by the physical requirements. So it's not that we are guaranteed that the object that we're going to have are not some mathematical construct that have no clear relationship to the physics. And this essentially solves all the problems that you might have of interpretation and all of that, because you start with the physical model. You don't start with the math and then you wonder what the math means. You start with the physical model. So at every point, you know what it is that you're describing. And the goal of physical mathematics is really to be able to look at any mathematical proof and read it, translate it in physics, so that every proof can be understood as some type of procedure, as some type of argument on the physical objects that you're modeling. And I hope to convince you that it's kind of transformative once you start doing things that way, because you don't have this mismatch between the math and physics that we currently have. Okay, so before we start, let's talk about what I call the fundamental misunderstanding in the foundation of physics, which is essentially the relationship between math and physics. The prevalent attitude among physicists, and it was also my attitude when I was out of university, because that's basically what you are taught, is that basically math is just a tool for calculation. And the technical details are better left to the mathematician, because there is no physics inside those technical details. It's just math. And Sabine Hossenfelder, in his Lost at Math, even though she criticizes the use of math in physics, sort of shows that she has this perspective as well. She says, but we don't develop theories by writing down assumptions and then derive observable consequences in a sequence of theorems or proofs. In physics, theorems almost always start out as a loose patchwork of ideas, and clean up the mess that physicists generate in theory development, finding a neat set of assumptions from which the whole theory can be derived, is often left to our colleagues in mathematical physics, a branch of mathematics and not physics. And in her mind, and in my mind 10 years ago, this is perfectly fine and logical, and this is how it should be. And even the ones in physics that work more towards the math have this attitude and then have this idea that you have to start using this mathematical structure that a mathematician give you because they're better, they're more precise, and so on. Like, there is a fundamental problem with this, is that we don't just use mathematics to calculate. We use mathematics to specify our models. And specifying the models is the whole point of physics. This is called, in math, mathematicians call this mathematical modeling. And they're perfectly aware that the mathematical modeling should be done by the people in the respective field, not by the mathematicians. Mathematicians create the tools, and then it's up to the people in the field understanding what the tools are, how should they be used, and how should they be applied to their respective field. And one of the fundamental problems is that there is no single way to clean up the mess, because once I give you a patchwork of ideas, you have to clean up using axioms and definitions that are precise, and each axiom and definition represents a choice in the mathematical modeling, which means a choice in the physics that you're going to be describing. And since there are many of these choices, mathematicians don't know the physics, so they can't tell you what is the correct choice to make. And this is something that mathematicians told me. Like, they convinced me that this is how it works and it has to work. So we have this fundamental misconception in physics of how math should be handled. And so we end up with the wrong math. It's math that mathematicians develop for their own purposes because it's convenient for them to prove theorems or to make calculation, but it's not the correct thing to do the mathematical model. And so before talking about physical mathematics, let's go through just a couple of examples of unphysical mathematics that we use, but it's not quite the right mathematics to describe the thing that we would like to describe in physics. So, for example, in differential geometry, if you study differential geometry in a math textbooks right now, not from 100 years ago, you have this notion of tangent spaces and tangent vectors. And the tangent vectors are essentially defined as derivations. So a vector is a map that takes a smooth function and gives you back a smooth function, and it has some properties such that map is actually taking the derivative along a particular direction. And in differential geometry, you use the partial derivative in every direction as a basis, and then you have components and you put those bases together such that you create the derivative in a particular direction. So now you can take this vector, give a function, and of course, this vector applied the function will give you a different function. And this is very useful to mathematicians because it gives an algebraic feel to this tangent space, and you can do some neat tricks. But the issue is this doesn't work for us because we have units. So how would this work, let's say, in polar coordinate? Well, we have a derivative in R and a derivative along theta. And these are the two elements of the vector spaces, the basis for our polar coordinates, but we can't sum them because this would be an inverse meter and this would be an inverse radiant, and we can't sum them. They don't form a vector space because we can't sum them. Same thing in phase space. You have a partial derivative with respect to position, a partial derivative with respect to momentum. These are incommensurable quantities. It's not even like here that you can kind of fudge it because you put some constant so that you make this a distance. No, here you can't because these are completely incommensurable things. So this doesn't work. And this is the first sort of lesson that you have here, that if something is mathematically precise, doesn't mean that it's physically precise. And even if you can make some sort of translation because you say, okay, yeah, well, but some of the physical objects that we are studying are actually isomorphic to this, and so you can make a map and so on. The problem of having all these steps in between make the math farther for the physics. And so every time you have to translate back and forth, and it creates sort of a cognitive load that you don't even realize that you have. And it's only after you remove that cognitive load and you start having definitions that actually map, you realize why I was doing it. Everything becomes a lot simpler. So this is something that, again, it's how we do differential geometry, and it's something that differential geometry is something that we use in physics a lot. And the reason why I was able to sort of decipher the action principle and lots of other things is because I said, well, let's fix this. Let's make something that is closer to the physics. And once I started doing that, then the physics intuition kicks in, and you start having conjectures, and then you can go back to the math and prove the conjectures and define things. So this is one example of physical mathematics. We need something like that. We need differential geometry, differential topology, but we need it with definitions that make sense to physics and they map well to the physics. And the mathematicians are not going to give them to us. We have to make them ourselves. Another issue is in quantum mechanics. In quantum mechanics, states are represented by a square interval function, complex square interval function. So, for example, this function here is a part of our Hilbert space, and it will give us a Gaussian distribution in position, and we can see that it integrates to 1, so it's normalized, and the expectation of the variance is 1/2. Also, this, it's still a sort of a bell-shaped curve, but the tails are fatter, right? This square root of 1 over pi y squared plus y. Also, this is a square interval function. So in principle, this is in our quantum state, and it integrates to 1. But you can see that the variance is infinite. And you should start thinking, well, do I really want variances that are infinite? And would these things make sense? And there is a problem with Hilbert spaces, because in Hilbert spaces, there is a theorem that tells you that every continuous linear operator defined on the whole Hilbert space is bounded. Therefore, any quantity, any observable that is not bounded, like position, momentum, energy, number of particles, cannot be defined on the whole Hilbert space, meaning that either the quantity sort of does not converge, like it's infinite, or it's not even well defined. Like it would be, say, one of those things where things keeps oscillating between positive and negative, and nothing converges. And so those objects are in the Hilbert space. And you could say, yeah, well, like any physicist does, we can just ignore them. Just take them out, and who cares? The issue is that you can create a coordinate transformation such that for one observer, the expectation is finite, and for another observer, the expectation is infinite. And that would mean that you are throwing out the states that are different from the ones that I'm throwing out. And that does not satisfy the principle of relativity. It just doesn't work. Even worse, in principle, you can have unitary evolution, therefore unitary time evolution, that move a state with finite expectation to one with infinite expectation. And again, these are clearly not physical. Now, these things don't happen in classical mechanics, because what you can do in classical mechanics is say, if I have a probability distribution, I can always cut it both in position and momentum. Like I can put a cutoff, and then my distribution has compact support. And if the distribution has compact support, I'm sure that all the expectation of all possible functions are going to be finite, because the maximum, and there's a maximum and a minimum for that function, so you're always good. In quantum mechanics, you can't do it, because if you take a wave function in position and you apply a cutoff, well, now you have a function that has compact support in position, and the Fourier transform of something that has compact support has not compact support. It's an entire function and spans the whole thing. So this is actually a problem, and which means that we probably don't have the right function spaces. There might be other function spaces where, like the Schwartz function, that would guarantee that all polynomial position and momentum are finite. But we physicists have to understand what are the requirements that we need to put on states, such that we can say, yes, we have valid states. So this is a situation that we have in the current state of the art. We have the physical world, which is our informal system of the things that we actually produce in the lab, right? They're well-defined physical objects because we can prepare, manipulate them, and so on. And then we have their mathematical representation, and we wanted to map these objects to these objects. Unfortunately, what sometimes happens is that we have objects that are well-defined and we map to things that are not well-defined in the math, or we start with something that is well-defined in the math, we do some transformation, we get something that is not well-defined, and then we go back and then we can't go back, right? And this is the current state of the art in theoretical physics. And I personally think that this is insane. Like we shouldn't have this. What we should have is this. We should have the physical world with a set of things that are well-defined, and then we have the mathematical representation, and we can go back and forth, and we know exactly where the limit of the mathematical representation and where the limit of the physical world in terms of the assumption that we're using, and we can go back and forth. And if you start doing that, you realize something, that since you have a set here, you're defining what are the conditions of the physical systems to have the mathematical representation. And then you have the set of mathematical objects. So you have two definitions here. You have physical specification and mathematical definition. What needs to happen for you to be able to make this nice map is that the physical specification has to be equivalent at the mathematical definition. So instead of mapping the object one by one, you're taking the physical specification, mapping it to a mathematical definition, and that's exactly the case in which we can make this map. So what we're going to say is that a mathematical definition is physical if you can do this, if it captures and only captures an aspect of the physical system. And ideally, we would like all the mathematical definition that we use in physics to have this property. And if you can't do it, then you need to fix it. And as I was saying before, you can only do this if you start at the lowest level of the system, of the mathematical structure. And most of physicists don't even know what are the lowest level of this mathematical structure. We're going to talk about topologies here. I don't know how many people that are here that come from a physics background know exactly what a topology is. But that's kind of part of the problem, is that there is this idea that one can do foundations of physics without having absolutely no clue on the foundations of mathematics. And it just doesn't work like that. Okay, so one of the things that we have to understand is how to do it, right? How can we are able to map, how should this standard of rigor go from physics? Like mathematicians have developed their standard of rigor for their discipline, but as we saw in physics, you sort of, oh yeah, you make a mess. We don't have standards of rigor. But if we want to do physical mathematics and we want to do it properly, we need a standard of rigor. And we need to define it ourselves as physicists, make something that makes sense to us, but then also gives to the mathematician something that makes sense to them. Otherwise, we're not really doing mathematics. We're doing physical mumbo jumbo. Okay, so how should we do this? And this is the setup that we have come up with. Again, it might not be the perfect standard, but it's what we have. And right now, it's better. It's definitely better than what we have. So, for example, let's say that we want to define an axiom, and we want to define an axiom on a space of ensembles. And if you're a physicist or an engineer, you know what an ensemble is. It's part of the statistical description of a system. And one of the things that you want to say that if you have two ensembles, you can make a statistical mixture, and the statistical mixture is yet another ensemble, right? So that you can always take two ensembles, make a statistical mixture. We have given probability, you're always going to get another ensemble. And this, again, if you study statistical mechanics, if you know what probability distributions are in the conception lab, this is an informal, intuitive sense. It's something that that makes sense to any physicist and an engineer. It's you don't need to explain to an engineer or a physicist that a statistical mixture of ensemble is an ensemble, right? But if you give this to a mathematician, they're going to tell you, I don't know what ensemble is. It's not precise. It's not This is what mathematicians are going to tell you. It's not precise. It's not precise. Okay. So you say, okay, mathematician, formally, an ensemble space is equipped with an operation plus that takes a number from 0 to 1, two elements of the ensembles, and gives you back another ensemble. And it's called mixing. And we note it with an infixed notation. And it has this following property. So now we have a formal requirement that the mathematician is going to say, now this feels precise. But of course, the physicist is going to say, okay, what is all these funny symbols? Why do we have them? And so we need to close the loop. And how do we close the loop? We need a formal justification, something that shows that the formal, informal, intuitive requirement justifies the use of this formal requirement. So it's kind of like a proof, and to a physicist, this might feel like a proof. And maybe if we went back in time in the 1700s, even mathematicians would have considered it a proof back then. But it's not a proof right now, because it's not all within the formal system. It takes elements of the informal system to justify things that you're putting in the formal system. So let's go through all of it, so that you can see how it works, and you can see the level of precision that you can get. So this axiom captures the ability to create a mixture merely by selecting between the output of different processes. So now we have a clear idea of what is being modeled. We have the two processes, and we are creating a process out of those two processes. So let E1 and E2 be two ensembles that represent the output of two different processes, P1 and P2. Here's P1, here's P2, and here's the output. Let SP be a process that outputs two symbols, the first with probability P and the second with probability P bar. Then we can create another process P that, depending on the selectors, output either the output of P or P2. All possible preparation of such a procedure will form an ensemble, because that's what an ensemble is the collection of the infinite collection of all the possible outputs of a procedure. Therefore, we're justified in equipping an ensemble space with a mixing operation that takes a real number from 0 to 1, the probability of the mixture, and two ensembles, E1 and E2. Okay, so now we have a clear idea of what it is that this plus thing is describing, because we know what it is as a model. Now we need to justify all these different properties. So we say that it's continuous. Then we say that given that mixing represents an experimental relationship, and all experimental relationship must be continuous in the natural topology, mixing must be continuous. Note that P is a continuously ordered quantity where no value is perfectly experimentally verifiable, and therefore the natural topology is the one of the real. This justifies continuity. Now, of course, you haven't seen all the previous parts that we have, but that's kind of the point. This is the point that I was saying before. If you want to have everything fully justified, you have to do it from the most basic structure. So we're going to have some justification from previous finding that if you have experimental verifiability, you have topologies, and experimental relationships have to be topologically continuous. And so we can use the previous result to justify our axioms. Okay, now we have to justify all of this. If P equals 1, the output of P will always be the output of P1. This justifies the identity property. In fact, the identity property says that 1A plus 0B gives you A, right? If P1 and P2 are the same process, then the output of P will always be the output of P1. This justifies the idempotent properties, right? So, and the idempotent property is PA plus P bar A equals A, which is exactly what's happening here. The order in which the processes are given does not matter as long as the same probability is matched to the same process. The process P is identical under permutation of P1 and P2, so we have commutativity. And if we're mixing processes P1, P2, and P3, as long as the final probability are the same, it does not matter if we mix P1 and P2 first or P2 and P3. And this justifies associativity. So there is the issue that you have sort of to take these and, oh, by the way, I didn't say that P bar means just 1 minus P. You have a lot of 1 minus, and it's just easier to put a bar on top. But then the issue is that now you have to prove that these numbers here, when you do the multiplication, are the same, and you can actually do it with just a little bit of algebra. And so this is the kind of thing that I think we need. And the thing is that it's totally possible and doable. So at this point, there is no question as to what the math describes. We don't have a problem of interpretation or stuff like that. The properties are justified by and are a consequence of what the model describes. So if we are describing that, you must have those properties. There is no way around it. And then the idea is that then every math proof can be understood through this description. So if you have 10 pages of math proof, in principle, every step that you have, you can go and say, okay, there is a process, I'm doing this, I'm doing that, and so on. And so the whole point is that the math now describes and only describes a physically meaningful concept. It's physical mathematics. It's mathematics that is representing something physical. And it's clear what is going on. Okay, so the goal of physical mathematics is essentially to record all of the mathematical structure that are used in physics in this way. It's a lot of detail, right? And it's a lot of bumping your head against the wall and trying to figure out what are the correct sampling points and why do we have them. But once you're doing that, you have a clear realm of applicability of each mathematical structure. So you know why do you have that linearity, right? That linearity that we had in that space was coming from this idea of mixing. And in fact, one can see that all the linear structure in physics actually are inherited from the linearity that we just seen of the mixing of statistical structures. So you really know where things come from. You get this perfect map between math and physics, and you can go and provide generalization for structures for all physics, because the fact that an ensemble, a statistical mixture of ensemble is still an ensemble, that applies to all of physics. It doesn't matter if you have a classical space, a quantum space, a quantum field theory, or even a theory that of quantum gravity that we don't know what it is. We know already that there's going to be some linear structure in that theory, because when we take statistical mixtures, we need to be able to have a linear structure there. So to me, this is just a better way to do physics. And you have to get used to it, because it's very different from what we currently do, where you just, oh yeah, let's try to use the group G24 and see what happens. It's a lot more details, and you need to be cognizant of a lot of nuts and bolts of how the math work, because you have to sort of select what are the correct nuts and bolts. But it forces you to think a lot deeper about physics. What it means to have an experimentally based theory, what it means to define a state, what the entropy is, what the energy is. And then suddenly, all these details become meaningful. There is no just a math thing. The topology is meaningful. The way that you make limits is meaningful. The convergence criteria is meaningful because it's connected to the experimental variability and so on. And so you get all these details, and you get this. Yes, it becomes a lot easier to have a better intuition in both the math and the physics. So these are the takeaway from this section is, first of all, is that it is possible to define starting points for physical theory so that they're both mathematically precise and physically meaningful and philosophically consistent. And this is the first surprise, because if you told me 10, 15 years ago that you could do that, I would have probably objected. And if you probably told me that I was going to do it, I would say you're crazy. Because you're trained for a long time to think that, math, physics is always going to be hodgepodge. And in some sense, it is true. But you just have to do it correctly. There is a way to do it, and a way that it works. And so this is the first part, you can do it. And so physical mathematics, the goal is to find mathematical structures that are justified by the physics. And this justification provides a new standard of rigor for physical theory. It's something that we currently do not have. And I really think that we do, especially if we want to extend physical theories to regimes that are not regimes in which currently physical theory work, because you don't know whether the math is going to work. And as I said, mathematics has gone to a more abstract path, which is totally proper for mathematics, but then it's going to bring in some things that are not going to be useful, not going to be physical for us. So only mathematical structures that are justified by unavoidable physical requirements can serve as a truly foundational structure. So this is where you see really the difference between the foundation, like the foundational objects as they're normally perceived in physics as, the fundamental constituents and the fundamental forces, the one for which everything else is an approximation. No, for us are the unavoidable requirements that are there in every physical theory. As I said, every physical theory is going to have ensembles because we need the statistical properties, because those are the ones that we actually go and measure and validate experimentally. And so all physical theory must satisfy those requirements. And so now these requirements can form that theory of the physical model, because now all models must at least give you that structure. And so again, the whole perspective here is that the foundation of physics is not just guessing what the physical world is made of, but articulating in a precise way what physical theory are and what are the things that we do, that we must do when we do physics. And this brings the foundation of physics, where frankly, a lot more in line to what the foundations of math and the foundations of computer science are, both conceptually, like in math, you want to understand what is math, what is a proof, and so on. In computer science, you want to understand what is computation, what things can be computed and what not, what are the classes of computations. We're going to want to be able to do the same thing in physical theory. Well, what is a physical system? What does it mean for things to be experimentally connected to experimental verifiability and so on? But it also brings it more closest in terms of the mathematical techniques that you have to use. As we're going to see, it brings in a lot more lower level logic part of things, order theory type structure, which are actually closer to what those other fields use. So it's all very interesting. Okay, so what we're going to do right now is actually see an example of a fully fleshed theory and a connection of experimental verifiability and topology sigma, which I talked a lot. So let's go and look at it at least briefly. So we want to start with principle, with ideas that basically tells us what is it that we're doing. And so we start with this principle of scientific objectivity that tells us the sciences are universal, non-contradictory, and evidence-based. So this means that science is about statements that are associated to experimental tests. So we have a statement, and it can be true or false, but then the statement is associated to an experimental test. And the experimental test is tricky because it can succeed in finite time, it can fail in finite time, or it could also be undefined. Like it could be something where you have no end. So for example, if I wanted to ask whether there is extraterrestrial life, I can start looking for extraterrestrial life. And if I find extraterrestrial life, I'm done. I found it. But if I don't find it, I can't terminate and says, oh, it doesn't exist. There is no termination condition. You have to keep going, keep going, keep going. And you can assume that, if there is, at some point, you're going to be able to find it. So you can assume that the statement is verifiable. If it's true, at some point, your test is going to succeed. But you might not be able to assume that it's also a falsifiable statement. That is, that if the statement is false, then the test is going to succeed, is going to fail in finite time. And so what we're going to do right now for the next 15 minutes is just understanding what this simple thing gives you in terms of a mathematical structure. And that's it. So again, one of the key elements that we also saw yesterday, it's finding simple ideas that seem trivial, but that have a very large set of consequences, and in particular here, they give you a rich mathematical structure. So if you look at the book, this whole idea is characterized in two sets of axioms. The first two axioms are what I call the axioms of logic. It basically tells you that there are statements and you have a logical context, and formally a logical context is just a set and the statements are just elements of that set. And you have a truth function, something that tells you this statement is true, this statement is false. So there exists a truth, and this is what makes science objective, that there is a truth and there is only one truth for everybody. Then you're going to have possible assignment, like you don't know what is the truth, but you know that there are some constraints. So for example, if I say that that animal is a cat. I know that it's not going to be a dog. And so if I assign false to one, I can assign true to one, I have to assign false to the other. So not all statements can be assigned any truth value because the statements have meaning, and the meaning prevents particular assignment. So we're not going to define meaning in terms of the mathematical structure because it would be too complicated. And so one of the thing that you have to do in physical mathematics is realize what makes sense to put in mathematical structure and what to leave out, and just leave it in terms of justification because it's more convenient. And then design the axioms such that they are easy to justify. So the axiom that we have here, like these three axioms, are going to be equivalent to say that you have a Boolean algebra, which is what you would define if you were doing logic mathematics. You basically just say, I have a Boolean algebra. The point is that justifying all the properties of a Boolean algebra becomes cumbersome, becomes not really intuitive physically. Instead, justifying this set of axioms becomes a lot more intuitive, and you can do it much more easily. And so that's why we have this idiosyncratic way of defining a Boolean algebra and the things that we have. And then we're going to have, we add the structure of verifiability without adding the test, because again, the tests are cumbersome, and you can't really fully formalize what a test is and how it works, because a test, at the end of the day, it's something that exists in the real world, and it has very, very many complicated features. So you just assume that there are some verifiable statements, so some statements that if they're true, eventually you're going to be able to say, yes, they're true with a test. And you're going to have now some properties of these verifiable statements that you can justify. And so let's, for example, take one of these axioms, the axiom of verifiability, that tells you that a verifiable statement is a statement that, if true, can be shown to be so experimentally. And again, this is the informal part. And now we have the formal part that tells us that each logical context contains a statement, and the statement, a set of statements that is a subset of the verifiable state of the full context, and those elements are said to be verifiable. So we're just declaring that there are some of these are verifiable. And then you know that every certainty is verifiable. A certainty is something that it's always true in every assignment. Every impossibility is verifiable as something that is always false in every assignment. And a statement equivalent to a verifiable statement is verifiable, because conceptually, these two statements are equivalent if they're always true or false at the same time. So if I have a test for one, then of course I can use that same test for the other case, right? And so this is the structure that you have. You have the context with all your statements. You have a subset, right? And this is in the formal part. And this, in the informal system, you have these experimental tests, which we're going to use in the justifications, but you don't use them in the formal side because it would be too cumbersome. You wouldn't be able to make really a good theory, and they're not necessary. So the fact that you can get away with it also tells you that they're not really so important. Just the important thing is that you can say that some elements are verifiable and some aren't. Then you're going to have another axiom that tells you that the finite conjunction is verifiable. So if you have finitely many statements and you have an end, a logical end, you can verify the logical end just by testing all the tests one at a time, right? So this is the procedure. You run all the AI. If they all succeed, they're all going to succeed in the finite time. Therefore, you're going to be able to reach step 2. And then you're going to return success. And if they didn't, if one of them failed, then you go and return failure. So you can write a pseudo code, a pseudo test to be able to show that you can, in principle, always do that. Now, for the OR, the structure is a little bit different, because if you have the disjunction, the OR, as long as one test terminates in finite time correctly, like if it succeeds, then you don't need to test all the others. You can disregard them and you just can return success. The only problem that you have to be careful is some of these tests might not terminate. And so you have to have a procedure that explores all tests for an arbitrary large amount of time. And so what you can do is that you initialize n to 1. So now you run the first test for 1 second, and if you succeed, you quit. Then if you don't succeed, you increase n and you go to 2. So now you're going to test the first 2 statements for 2 seconds, and if you succeed, you finish. If you don't, you go back to 1 and you increase, and so on. You keep looping. You're looping. At some point, this procedure is going to test all your statements for an arbitrary large amount of time, and of course you're going to find it, right? So it still feels like a proof, but it's not a proof because we haven't defined what these tests are and what a procedure is and so on. So it remains part of the justification. But the important thing is that you can only do a countable collection, because if the collection is uncountable, you can't find the test that terminates. So it still feels very mapsy, right? But it's a justification of their axiom. And these are the type of things that you also have in intuition and logic, where you have similar type of axiom structure, because that's the type of logic that we are doing. So what you can do at that point, you can say, okay, now I have a set of statements, and I can say that these statements, D is generated by a basis, by a set of statements. If I can reach every statement in D by this finite conjunction and countable disjunction. So that basically, I only know how to test B, right? I have the test defined on B, but now all the verifiable states in D can be constructed from the tests of B. So everything is explorable just by exploring the basis. And so you define experimental domain as a set D that is generated by a countable basis, because that's what you can test. If I even give you an infinite amount of time, right, an arbitrary large amount of time, which is not infinite, an arbitrary large amount of time, you can only create a procedure that can explore countably many. And so that's the most that we can explore experimentally. And so now we know that every sort of realm that we can go and experimentally explore has to be one of these things. There's a set of verifiable statements that have a countable basis. From this, then, you can generate a theoretical domain, which includes all the statements that have the test, regardless of termination. So this does not add the new information. It just adds new statements that are still well-defined physically because they have an associated test. And then you can define a possibility as essentially something that tells you what would be the statement, the truthfulness or falsehood of all the statement if we knew that that possibility were true. So, for example, if you have the set of all possible measurement of mass, right, and the verifiable statements would be the mass of the electron is greater than I don't know, than 0, but less than 1 electron volt, right? That would be a verifiable statement. And if I knew that the mass of the electron were precisely one number, I could tell you what all the verifiable statement would be true or false, because I would just see whether the actual value, the true value, is within that range. And so the possibility basically is that it's the mass of the electron is exactly this number with infinite precision. And it turns out that these are actually statements within the theoretical domain. And so you end up with this correspondence. You have your verifiable statements here. You have the theoretical domain, which is all the things that have a test. The possibilities, which are the experimentally defined case. So the mass is 1, the mass is 2, and so on. And what you can show is that there is an isomorphism between this and topological spaces. The points correspond to the experimentally well-defined cases, like all the possible values of math. The open sets represent the verifiable statements, so the things that are connected to experimental verification. And what are called the Borel set now represent all the theoretical statements, the things to which you can associate tests. And then you have this perfect map. If you have a statement, the statement can be understood as a set of possible cases where that statement is true. The interior, topological interior of that represents where the test would succeed. The exterior would represent where the test fails, and the boundary, the topological boundary, represents the part that remains undecidable. And An open set is a verifiable statement. So if you have a range of mass, you can say the mass of the electron is within that range. A closed set, like at a single point, the mass of the electron is exactly 510 kilo-electron-volt. That's not a verifiable statement, but it's a falsifiable statement, because if I verify that I have a range that excludes that, then I can do it. And then there are other Borel sets, like the set of all the rationals, right? This corresponds to the mass of the electron in kilo-electron-volt is a rational number. This is, in principle, it's a statement that makes sense, but it's undecidable, and you can see that it's undecidable physically, because you're never going to settle this, because you would need infinite precision, and you're never going to get infinite precision. In topologica, you can see it because this set has no interior and no exterior. It's basically all, the boundary is the full space, which means it's an undecidable statement, because the corresponding test is never going to terminate. So you can make this map, again, precise, and then you can get notions of limits and all of this. But the thing is that you can, with just this simple idea, you can make sort of very broad, you can find very broad consequences. So if the set of distinguishable case E comes from countable limiting tests, then each point can be represented as a string of false and trues, and which also means a string of zeros and ones, but a countable sequence of 0 and 1 can be understood as a binary expansion of a real number between 0 and 1. Therefore, the set, the cardinality of the possible cases that we can distinguish experimentally cannot be greater than the set of the real numbers, which means issues about higher infinities, large cardinals and stuff like that you have in set theory, you're going to say, well, we're never going to care about that. And probably intuitively you would have said that, but now we know why. Like, there is a reason why we don't care about cardinality greater than the continuum. And things like the set of all discontinuous functions from R to R have cardinality greater than the continuum, and therefore they cannot represent physical objects. And again, this would be intuitive to a physicist, but there is an actual reason. Like, it's not that, oh, you know, there is a hodgepodge. No, there is a precise reason. A reason is why that's the case. Another thing that this justifies is we really have a physical understanding of what the Borel sets are the sets that have associated with tests. And so when we create probabilities and measures, we have to use those sets, because those are the ones that are physically meaningful. And this essentially tells us why we don't have problems like the Banach-Tarski's paradox that there is in math, and physics is sort of protected by that, because we don't use all the sets. So if you don't know what the Banach-Tarski paradox is the idea that you can get a set of, you can get a ball and divide it into at least 5 parts. You recompose those pieces into 2 balls of the same size by doing a transformation that in principle preserves the sizes, right? And this is basically tell you that it's basically impossible to define a measure on all the possible subset of Rn. And again, these problems are avoided because, well, all those sets that are non-Borel sets are not physically meaningful. And therefore, we don't have to talk about them because they're not physically meaningful. And therefore, we solve these problems. So again, this is where knowing the foundation of a little bit of foundations of mathematics is useful to understand what needs to happen in physics, but also the reverse, right? That this physical mathematics can give us insight into these foundational issues of mathematics, at least, you know, how they're solved for physical theories. Another thing, we start running out of time, so I have to be quick. Another thing that you can find is that the causal relationship you have, if you have mapped between these spaces, they have to be topologically continuous maps. But topologically continuous map does not mean analytically continuous map, because again, the topology is defined by what we can measure and what we can verify. So, for example, we can verify that we are at a triple point if we have an equilibrium of the 3 phases of liquid, vapor, and solid. But we don't do that by measuring pressure and temperature. We do it in a completely different way. We have a different way to verify. And then we can say, okay, we are here. And now that means that that region, any phase transition, that it's a region of phase transition, becomes topologically separate, because you can say, oh, I am on this line, no, I am on this point, and so on. You have a different way to verify that you're actually on this line, on this point. And if you have, you can have now analytical discontinuity over phase transitions without breaking topological continuity. So the idea is that really this definition works very well even at these extreme cases, and again, they give you even insight of why you would choose the triple point as a starting point of defining temperature and so on. So again, the main takeaway here is that requiring experimental verifiability in a physical theory leads to a topology as a sigma algebra. Every set of distinguishable cases or physically well-defined cases is a T0 second countable topological space. And open sets correspond to verifiable statement, continuous function preserve experimental verifiability, and Borel sets correspond to statement associated with tests. All the proofs can be understood now as describing argument on experimental verifiability. So limits are defined on top of the topology. Then you're going to have a truth sequence of verifiable statements that become a constant. That's what a limit is. Right? At some point, I say, yeah, that thing is true because it keeps being true and it will always be true. A topological distinguishability, the separated axioms become experimental distinguishability. How well I can distinguish two statements and say that if one is true, the other one is false. And as we saw, the interior and the exterior and the boundary become the verifiable, falsifiable, and undecidable fact. So so the point is that once you have a good understanding of what the foundations are, then it's easier to understand why the constructions that are on top have to be done in a particular way. So probability measure in general measure theory are defined on the sigma algebra, on the Borel algebra, because we assign probabilities and sizes to statements with tests, right? So if you can't, this also tells you, like, if you for people that are talking about hidden variables, right? How you are going to assign probability to hidden variables if you don't have a set of experimental tests that you can associate them with? What are those probability actually meaning? It's not what we mean in physics, that's for sure. Or you can also have the notion of topological groups. Then these are groups of transformation, usually groups of transformation, that we can experimentally define and identify. That's why in physics, if we have a group, it's going to be a topological group, because the elements have to be experimentally verifiable. You need to be able to know what transformation you have. So again, the main takeaway should be that it is possible to develop a foundation of physics that is both mathematically rigorous and physically meaningful. That we are able to make this map. We're going to be able to say, yes, we have statements that have tests, and then we define, we correspond them here. We have all our axioms, and then we can find topologies and sigma algebra in a precise way. And again, no issue of interpretation, and you know when the tools of mathematics are applied and if they're applied correctly. And it should be clear, hopefully by now, that there is no just math. That thing just has to go from your head if you have it. There is nothing that is just math. Either the math that we're using in physics represents physical objects, then it's describing physics, and it's not just math, or it doesn't. And the theory should be stripped away from the physical theory because it's just cumbersome stuff that shouldn't be there in the first place. And only by understanding the full details of the math and the physics, you can make that determination. So you can't just say, oh, it's just it's the job of the mathematician, because it doesn't have the physics part. And if you're a physicist and you want to do this, you have to become at least knowledgeable enough to be able to talk to experts such that you can make the translation and understand what you need and what you don't. And unfortunately, a lot of people that work on a foundation do not know these issues in the foundation of math. And so if you do not know what the well ordering of the reals is, right, you are precisely the person that cannot determine whether it's physically significant or not. So if somebody says there is just, this is just math, and doesn't know exactly what the math is, he's really the person that can't not make that value judgment. Okay, so wrapping it up, assumptions of physics, it's a different approach to the foundations of physics. Again, there are no interpretation, no theory of everything. We just have a physically meaningful starting point from which we can derive the laws and the mathematical frameworks. And physical theories are just models, and therefore we just need to be clear of what that model is describing and what is the realm of probability and so on. And physical mathematics wants to do this very precisely, such that we can derive the math required from the physical requirement, from the physical models that we have in our head. And in physics, mathematics is used to make, to model physical system, and therefore we need the mathematics that is designed specifically for that purpose. Issues of large cardinals and all the hierarchy of infinity is fun, but it's clearly just math. That is just math. It's not going to be useful to define a physical system, and we need to understand what parts of math are useful or not. And again, you need to start at the lowest level of mathematics, because rigor, precision, meaning, correctness cannot be sprinkled on top. So if you don't know the foundational layer, you don't know what the top layer is. And I'll leave you with this Gall's law: big system that works evolve from a small system that works. They never come from big systems that do not work. So the only way to do this is to retreat to the smallest thing, understand the smallest thing, and then making a little bit bigger by keeping this full understanding. I have no idea how long it's going to take, but this is the only way to do it. And I think I am done.
All right. We've got a few questions in Q&A already. Leandro asks, what are your thoughts on Nivaldo Limos's reply to your paper in his article, Are Hilbert Spaces Unphysical? Hardly, my dear, which appeared on Foundations of Physics in the end of May. He asserts that your pivotal charge against Hilbert spaces is that by a change of variables, which is the change of basis unitary transformation, one, quote, can map states with finite expectation values to those with infinite ones. In the present work, it is shown that this statement is incorrect and the source of the error is spotted.
Yeah, we are preparing a one-page reply. Actually, a person in the a student that is following the project is actually spearheading that effort, because I didn't have the time. The response is quite simple. So he claims that a coordinate transformation is just a change of basis, and therefore it does not change expectations of the variables. And this is clearly false. If I do a translation, the value position better change, because if it remains the same, I have done nothing. The problem is that in the transformation, he both changes the state and the system. Like in a coordinate transformation, you can make an active transformation where you change the system but leave the variable the same, or you can do a passive transformation. You keep the system the same, and you change the variables that you're using to describe the system. He changes both. Of course, if you change both, nothing happens, but that's not a coordinate transformation. It's the thing that is staggering to me is that he contacted me and I told him this point, like, this is how coordinate transformation work. It's not something that I made up. If every, even when you do classical mechanics, it's like that. When you do, coordinate transformation on a manifold, that's what you're doing. You are changing the local chart. And the fact that it was published in a journal is very surprising to me, because again, it's undergrad stuff. So yeah, so we are preparing a response, and as I said, to me, the thing is so trivial that I didn't want to waste time with it. I just wanted to do other things, and then I said, basically in our Discord, if there is somebody that that wants to write this, and I tell you what you basically need to find, you're going to be author, and we respond to this. And one person, Robbie, decided to take this up. He brought up an excellent first draft, and he found a textbook that basically just says that, and we're going to respond for a letter soon, I think. So that's how it works. And again, it's very disappointing that this is the level of conversation on the physics journal on the foundations. And I'll make a video at some point about this thing specifically. Like the purpose of journals should be to sort of make the discussion proceed by sort of, okay, you know, this is something that has been already settled like 20 years ago. We're still in the foundation of physics, and of quantum mechanics specifically, talking about coordinate transformation. As if this is not has been settled like, I don't know, 100 years ago. I don't know, I find this. I don't have a word even, so.
Next question is in fact from Robbie. In quantum mechanics, could it be that Hilbert space is the correct space for physical states, and that there's something unphysical about the operators that are not defined on the whole space? If we could modify the position operators that it is defined on the whole Hilbert space, wouldn't that fix the problems with expectation values?
Well, that's where you have to define what a state is, because most of the time the state is defined in terms of measurable quantities. So if your measurable quantities are not well defined, then neither is the state. You know, that's the whole thing. Yeah, that's it. So to me is either you have a different way to identify the state that is not through the measurable quantity, like in the example of the triple point, right? You identify the triple point not because you're measuring the pressure and the vol and the temperature, and you say, oh yeah, I'm at the triple point. No, you verify the triple point because you're verifying that you are at an equilibrium of the three different phases. So if there are different ways that are not the statistical measurements to identify the state, then sure. But in quantum mechanics specifically, I don't see anything else, especially on the continuum.
Let me go, since it's a little bit more related to a question in the chat from Luther. The direct delta function isn't a physical object? Just with regards to
again, it's definitely not a state, because it would mean that you have so the delta function in quantum mechanics is problematic. It's very problematic because it's you know, we talk about a uniform distribution in momentum when you have a delta Dirac in position, as if that's something that is sort of probabilistically well defined, and it's not. This is something that, again, when I started working on this project seriously, I started basically auditing a lot of math classes to sort of be able to talk to mathematicians in a precise way. And you know, at that time, you know, I was used to thinking about, yes, uniform distributions on momentum, and then of course the professor starts talking about that these are like, they don't exist. This is the problem of the mass escaping at infinity, because it's a known problem that it can't be solved in probability theory, essentially. And of course, he doesn't know quantum mechanics. He doesn't know that some people are saying these things. And I said, oh, okay, that really doesn't work. And this is kind of the same problem that I was having before. We were saying before, if you take a function that has a compact support, has a sort of an infinite spread in momentum, so that he has to get all of this. So yeah, as a state, it really does not. Again, it would mean that you would have an infinite energy, an infinite spread in momentum. It just does not make sense. It can be a convenient mathematical tool to you know, to do some things, but you have to understand that it's maybe the limit of something. And so, for example, delta Diracs are very, very useful when you do signal theory and control theory, because they have essentially it's like they have a component in every frequency, right? So if you have a system and it's a linear system, and you want to characterize the frequency response of that system, what you do is you send an impulse, and then the output, right, is essentially the response of the system on all the frequency. So you take that output, you do a Fourier transform, and you basically have the frequency response of the system. So it's a really great thing, and then you're mathematically you can get this result precisely. But of course, you're going to think of the delta Dirac as a limit of impulses that are shorter and shorter and shorter, right? And then you take the limit not as something that is true, you take it as a limit. When you're doing physical mathematics, it's very important that you understand what objects in the model you think are physical, and like they're things that in principle you're assuming that you can prepare, and the things that are actual limit, right? And you may take a space and you say, okay, this is the space, but for convenience mathematically, I add the limits and I do things on the limits. You can still do it as long as you are able to make that distinction. So you could even say, look, I start with a physical space, like that it's not going to be the Hilbert space, it's going to be smaller. And then I say, that's the physical thing, and I know what the physical things are. But then, for convenience mathematically, I complete it in the inner product, and I get a Hilbert space. I do the mathematical calculation in the Hilbert space because it's more convenient. And then you get the result. As long as you're guaranteed that the result that you get of the final calculation is still on the set of objects that are physical, right? It's a little bit like when you are doing complex analysis as a stand-in Fourier analysis. So you have an equation or an integral that you have to solve on the reals. On the reals is complicated. You pretend that the variable is complex. You make the integral, and then you go back to the real number, right? You can still do it. It's a mathematical trick. You can do it. But again, the problem here is not what am I doing during the calculation, is what I'm doing during the modeling. And I want to make sure that every element in the modeling makes sense, and all the steps in the modeling make sense. And then I can go and expand through calculation. And this is, I think the problem to me is that if you are not worried about a calculation, but you're worried about issues of interpretations and the meaning of the theory and so on, you should be working on the physically meaningful subset, not on the extended subset. And this is why we have a lot of problems, I think, in the foundation, that we can't make that distinction.
But Braz's question in the chat whether a participation certificate will be sent. We had not been planning to, but if that is helpful, we can do so. Wasn't sure if Ibras had to sign off, so I wanted to answer that right away. So I've made a note of that.
Yeah, only to the people that are actually live, and you can see that they were in
the Zoom.
The Zoom, yeah.
Yeah, YouTube, we don't have any information about who's streaming it. Moving back to the Q&A, there's a question from Thomas. Has any work been done on the physical justification of Clifford or geometric algebra? What could physical mathematics have to say about vectors and more generally multivectors? So
I have, and we're going to see it tomorrow in the open problems, that I do have a starting point on what is a derivative, what is differentiability, and all that, and essentially forms and all of that, and how they can map. It needs to be closed, like it needs to become like a serious mathematical theory. Right now, it's a good thing for, let's say, again, for understanding what is it that they're doing and having a nicer notation for doing the math, and so that we can understand what happens. I do not have a full, but what I have is going to be more similar to what differential topology has than what Clifford algebra have. The problem with Clifford algebra is that they basically put things with different dimensionality in the same space. So, conceptually, you can imagine that you have points, infinitesimal lines, there are vectors, infinitesimal surfaces, there are bivectors, infinitesimal volume, three vectors, and so on. What Key-flow algebra do, at least what I understand that they do, is they put all of these together such that you can define a product that essentially takes, say, two lines, and it gives you both a point that represents the scalar product and a bivector that represents the area. And that's precisely what I don't want to have. I want always to be clear which are objects of the different dimensionality, because again, physically, you can't really sum lines with areas, like numerically, you can't sum them. What the Clifford algebra does is that they're not really summed, like you're still in sort of the sum of those spaces. But then again, what is the topology that goes across these things? It becomes a very quirky. I think you can get a similar result that map better to the physics by using the notion of differential topology. And also my issue is that I need to take all these things and be sure that they work in infinite dimensional spaces. So the way that I'm defining these forms and so on are things that hopefully, and this is the part that needs to be checked more carefully, can generalize well to infinite dimensional spaces, so that we can talk about, let's say, a metric tensor in quote in an infinite dimensional space, which is something that you really can't do, for example, in differential geometry, because you what's it called? You're finite dimensional. Manifolds are finite dimensional. That also, of course, opens a complete can of worms, because there is no good theory or unique theory of Lie groups, let's say, on infinite dimensional spaces and so on. So there are like lots of problems on the math side. But again, this is where I think the physical mathematics should give us more constraints than the math has, such that we can actually find the good structure. So the short answer is there is going to be something that plays the role of differential topology, differential geometry, and Clifford algebra, but it's not going to be exactly that, because again, those mathematical definitions weren't thought with the idea of working in all the type of spaces that we need in physics.
All right, let's go ahead to Daryl's question. Can you explain why the countable disjunction can terminate in finite time?
Yes, so that's basically a trick. So imagine that you have a test. The whole idea that you have a test, it means that it's repeatable. It means that you can do it however many times you want. So if you have a test that it hasn't terminated in 5 minutes, you can always stop it and restart it later, right? That's basically it, because otherwise the test wouldn't be repeatable. You wouldn't be able to start again and again. Okay, so if I have now countably many statements, let's start with finitely many statements, right? I need to be able to test, I need to be able to check. Let's say that I only have 2 statements. One of them will terminate in some finite amount of time, but the other one, let's say, that never terminates, okay? So what I can do is to test both of them for 1 minute. And if neither of them terminated, I can test them for 10 minutes, and then for an hour, and then for 5 hours, and so on. At some point, the one that will terminate in finite time, and so will hit the finite time that is required for the test to terminate. And then since it's an or, right, it's A or B, as long as one of the two terminates correctly, then you know that the disjunction is true, and so you can terminate. Now, this works for 2, and with 5 you can also say I test 5 for 1 minute, for 2 minutes, and so on. The problem is that when you have countably many, you can't test countably many for 1 minute, because it's already an infinite amount of time. So you first test the first for 1 minute, then they test the first 2 for 2 minutes, the first 3 for 2 minutes, the first 4 for 4 minutes, and so on. This is a diagonalization process. in the foundation of mathematics, a lot of the simple, like the thing is a fundamental level, the fact that, for example, that the reals are not countable and so on, you use this type of diagonalization. So it's a basically standard math technique. And so by basically saying, I take the first one for 1 minute, the first two for 2 minutes, the first three for 2 minutes, and so on, you are testing all tests for an arbitrarily long time. So at some point, if there is one test that terminates infinite time, at some point you're going to test it, and you're going to test it sufficiently long, you're let the test run for sufficiently long that it will terminate. At that point, you're going to find that one test that terminates, all the other things, it's a disjunction, it's an or. As long as one thing terminates, the whole thing is true, and then you can quit. And the only requirement is that you have countably many. So if you had uncountably many, like the continuum, you wouldn't be able to have this sequence, so you wouldn't be able to find the correct test. And what is interesting even here is that when you make a sigma algebra, right, the thing where you define a probability and you define measure for, and which I'm claiming this is an algebra of tests, the closure in terms of unions and intersection of sets, which corresponds to the ends and the or, because the union of the two sets is the or and the intersection is the end. It's required only on countable operation, which is exactly the type of operation that you're guaranteed to be able to make within algorithms. So all these things sort of map together too cleanly to basically say, oh, it's just a coincidence, right? This is what we are describing. So I hope it made it clear.
I have 4 open questions. I think we might be able to get through all of them, but might need to move a little bit quickly with relatively short answers. So Marwan Mohammed asks, what do you think about the 6th problem from the list of 23 problems by David Hilbert, which is about axiomatizing physics? How can it be related to the project?
So basically it's what we're doing, but it's not at all what he envisioned. He envisioned, again, we're going to formalize the one true theory, and everything else comes out of that. And we basically say, yeah, you can formalize it, but not like that. So in my mind, we are solving his problem, but not the one that he stated, the conceptual one of axiomatizing mathematics, physics. Yeah.
The next question is from Xinyue. Usually topology is introduced by abstracting concepts of boundaries and sets on continuous space, like our physical space. What's the connection here with topology introduced from experimental verifiability?
Right, the open sets are the thing that you can experimentally verify. And that basically gives you that notion of neighborhood and closeness. So if you have a point is a possible case, and a neighborhood, an open neighborhood of that point becomes a verifiable statement that is true if that case is true. So a point could be the mass of the electron is 1, an open neighborhood is an open interval between that. That's going to be a verifiable statement. And with this connection, you can re-understand all the notion of limits, convergence, continuous transformations in terms of experimental verifiability, because now you know how to translate. So it would take time now to do it, but you can absolutely do it. And you would have an introduction to topology that it's grounded in physics.
Next question is from Daryl. Do you see a possible scenario where the foundation axioms are too restrictive? If yes, how do we tackle this problem down the line?
Say it again.
Do you see a possible scenario where the foundation axioms, so our axioms,
our axiom,
I believe our axioms is the intent, are too restrictive? If yes, how do we tackle this problem down the line?
So if it's too restrictive, it means we watch the axioms. But it's going to be true, like this is where having to write the justification actually helps you see whether the axiom is too restrictive or not. Because when you write the justification, you realize, oh, I have to justify this. Where do I get it from? And that's when you realize that the thing that you're requiring is not always going to be there. And if you think that it's always going to be there, and in 50 years somebody realizes, oh, that's not true, then what happens is that you're going to change the axioms to a definition and have the more general axiom. But you are going to be able to, since you have the justification, you're going to be able to make that evaluation a lot more, how can I say, top of the mind. Like you actually know what you're doing. While right now you just put a mathematical axiom, you have no idea what is implying, so you can't even know whether it's too restrictive or not. And by the way, it happened to me while I was justifying axioms. I realized that they were too restrictive and that I couldn't justify those. So.
Okay, the last question is from Robbie. In quantum mechanics, we do not measure eigenstates of the position operator, delta Dirac, because we cannot be infinitely precise. Wouldn't it be more appropriate to have a position operator whose spectra is physical states that can be prepared in experiment? And then there's some discussion afterwards about whether we can measure any eigenvalue with infinite precision, but then it's noted that we can measure number of particles, so discrete quantity, and that the number operator is also defined on the whole Hilbert space.
Right. So again, this connects to the Borel sets and so on. Like if you think classically, all your statements are these Borel sets, and then you can check whether something is in the Borel set or not, right? And the point, you can think it as this interval that becomes a closed interval that becomes infinitely small and then becomes and picks a point. The same thing happens in mathematics with the Hilbert space. So what you can do is that you can think of, instead of just a position operator, you can think of all those operator that gives you 1 on a Borel interval and 0 outside of the Borel interval, right? And that would basically mean the particle was within this range or was outside of the range. If you do things mathematically correctly, right, to get your probability distribution, that's what you already do. So, you know, people in quantum logic are going to talk about these projections, and then you have a whole lattice of projection operator. You assign the probability to all these things, and then you get the probability measure, right? And so it's not, it's already done. Let's just put it like that.
That is all the questions in the Q&A. It is 11:27 Michigan time. So you might, I don't know if you want to take a minute
Yes.
between the sessions.
I'll fill in my bottle of water.
Yep.
Should we start?
Yeah, it's 11:30. I think you can get started.
Okay, so let's start the next session. And in this session, I'm just going to give you a set of results that we have from physical mathematics. Some are, well, let's go and see what they are. This is, first of all, an overview of, this is an old picture that I still have. I don't quite know whether it needs to be retouched or not, but the general theory is essentially still in my head is made of 3 layers. One is the one that captures the notion of experimental verifiability, the fact that we have tests. And this is the part that is basically very solidly done. Then there is another part that should define essentially what is the information content of the statements, because this is what you can basically show that geometrical size and probability and information content, they are basically all things that you can go from one to the other. And so there might be a layer here that can be constructed in a way that is general, and it should also be the layer that defines the units and physical dimensions and all of that, because all those things are not like knowing that there are statements that are verifiable is not enough to tell you what units are. And so there could be a layer in between here that it's sort of above experimental verification. It tells you something more, but it's still not defining states, processes, and stuff like that. I always need to remember to do this. There we go. Otherwise, the cursor disappears, and it's very nice. And so this part is basically the part that we're going to take some parts from here. And this part is not very well developed at all. This part is actually more well developed. So I'm going to give you some results from there. So as we saw in the previous part, we have this notion of experimental verifiability that leads to topologies in sigma algebra. And what we're going to look here is that we can use this to define quantity from references. So again, we need to construct everything. So we need also to construct the real numbers and have physically meaningful assumptions that are modeling something that gets us to the real numbers. And the idea is when you create a reference scale, you have some references that define a before and an after, and then you basically find some conditions on those references such that that scale, the reference system, is going to define a real number. And then we're going to talk about, instead, the new work that we're doing on ensemble spaces. Some parts are, some results are done. At least they prove and work well. Some other parts are instead to be cleaned up. And so I'm going to talk about this partly today because there are some results, and also partly tomorrow because there are open questions there, and I'm looking for people more on the math side to help me on those things to create essentially the structure that we need. So let's go and look at the reals. And this is like, to me, is probably the hardest bit of thing that I had to prove because yeah, it's you have to start with just this idea that you have these true and false, and you have these statements, and somehow you have to recover that there is an order and that you have the real. So in physics, we use real numbers to model physical quantities, and we actually need them. Like there are some people in the foundations of math that hate the reals, hate the axiom of choice, and all of those, and so they they try to really work without the reals, and there are substitutes for the reals to do some things, but as I said, we are not assuming that the real numbers are going to exist in some, physical, ontological sense. They're just in the model. And as a modeling tool, they're very useful because without the real, you don't get exponentials, you don't get Gaussian, you don't get like trigonometry in the trigonometric functions, and you use those all the time. So yes, it's going to be an infinite precision. Infinite precision is an idealization. We just need to understand what is the realm of applicability of that idealization, such that we don't pretend that we go outside of the space. Right? That's basically what we want. Mathematically, there are many different ways to construct the reals. So it seems that it's like a mathematical sport to create your own ways to recover the reals. And there are lots. A lot of them are based on algebraic properties. So you see the reals as a field, as something where you can do addition, subtraction, multiplication, division with some properties. So those are the axioms, and then you recover the reals. You can see it as a Cauchy sequence of rationals. So you first, this is inside theory, for example, that's how you define the reals. You define the natural numbers, then the integers, and then the rationals, and then the reals as either Cauchy sequence or Dedekind cut of rationals. And if you have never seen those constructions, well, I'm not going to be able to talk about it right now in details, but that's sort of how you do it. And the issue is, how do we define them? Like, what is the proper way for us to do it? What is it that we should be modeling? And the most fundamental structure that we want to have in the real is, again, the topology, because that means where you're going to be able to say, the mass is between this range and so on. So as a first thing, we want the topology, also because when you go and study manifolds, for example, everything is defined in terms of a topology, and all the transformation that you might have are not going to be linear transformation. And so they're going to destroy essentially the field, the algebraic structure, because the sum of 2 points in one system is not the sum of 2 points in the other coordinate. So really the field structure is not the correct one. So what is the correct one? Well, if you look at topology and the topology of the real, you essentially use the order topology. The order topology is basically defines that all the set of something is greater than A or something is less than B, right? All these sets are open sets. And all the other open sets are generated by these by countable, arbitrary disjunction and finite conjunction. And so this means that the object is after A and the object is after B are verifiable statements. And we don't know about the size. We just have references, and we're going to say, oh, it's beyond this reference and before this reference. And this really intuitive makes sense. Like if you get a ruler, we see all these notches. If we have a time, we have the clicks of the clocks, right? So this is essentially how we define quantities in physics. So it's very natural to say something is before, something after our references. So that's what we want to model. And so now the question is, can we can we characterize the reals only as a type of order? And it turns out that you can, and that's what Cantor did as a characterization of the reals. And it's very beautiful because there are not very many requirements. So unfortunately, I can't introduce order theory perfectly, but there are these essentially two facts that Cantor proved. First, that every countable, dense, linearly ordered set with no ends is automorphic to the rationals. So a linearly ordered set is one where you have elements that are always one after each other. So there are ordered sets that are not linearly ordered. For example, you could imagine to take a plane and define a direction, and so you can say that a point after this direction is going to be before a point that it was before along that direction. But then you're going to have 2 points such that none of them is before the other, right? Even in special relativity, you have light cones. Light cones define a causal order, but then you have 2 points that neither of them is in the light cone of the other, and therefore they're not ordered. There's no causal order between them. So not all sets are linearly ordered, but the reals are linearly ordered, the rationals are linearly ordered. So suppose that you have a linearly ordered set with no ends, meaning that there is no greatest value and there is no smallest value. And then it's countable, meaning that there are countably many elements. You can make a bijection with the natural number. And it's dense, meaning that between every two sets, there is another one, right? And between those two sets, there is another one. And between those two elements, there is another one. Between those two elements, again, there is another one, and so on, right? And so every order that has this property is linear with no end, it's countable, and it's dense. It's isomorphic to the rational, meaning that you can make a bijection with the rational such that if something is before another one in one order, is also going to be before the other one in the other order, right? And this is nice. It means when we have countably many points, linearly ordered, dense, those are the rational. So that's the first thing that Cantor proved. The other thing is the idea of a completion of a linear order. And the completion here is a little bit complicated. It has to basically be with supremum and infimum. If you get a set, you can always find a smallest greatest value or a greatest smallest, a greatest smaller value, right? You can basically bound it with two elements of the set. So, for example, the rationals are not complete because if you take the set of all the elements that are less than pi, right? There is no greatest element there is no smallest elements that is greater than all of them because you're missing pi. You're going to have lots of things that are greater than pi, but there is not going to be a smallest one. And so the rational, the reals are the completion of the rational, meaning that they fill all these gaps so that you always have the supremum and the infinite and the infimum. And basically it's a theorem in order theory that every completion of that every order can be completed and every completion is unique. Therefore, the real is the completion of the rational. So now this means that every complete linearly ordered set with no ends that has a countable dense subset, which would be the rational, is orderly homomorphic to the real because this set is the completion of the rational. So whenever you have something that is ordered and you can find countably many points in that order that are dense and the order that before was complete, then you get the rational. So that's basically one of these results that again are in the foundation of mathematics that we need to actually justify and do the things that we need. And so now we need to essentially make an argument, and we're not going to have time to go through the full argument, at least we want to give you an idea of what are the things that we need to put at the beginning such that we can recover the reals as being disordered. So how do we order things experimentally? How do we define order and quantity? Well, we have a way to compare two things and say that one is bigger and smaller than the other. Note that exactly the same is a little bit more difficult. If you have a scale and you put something that is heavier than the other, you will see the scale tip. But the scale might remain the same even if the two weights are not exactly the same, right? So it's a lot easier to say that things are before and after, where the things are exactly the same is a lot more difficult. So we're going to define a reference, which is going to be a tick of a ruler, a notch of the clock, or a sample weight on a scale. There is something that allows us to distinguish between a before and an after, right? And these references are fat, they're not infinitesimal. So you could be before, you could be after, or you could be on, or you could have something that it's a little bit before and a little bit on, a little bit on and a little bit after, or before, on, and after. And we want that after and before to be verifiable statements because those are the things that we can actually consistently verify. We can make a cutoff and say, yeah, we're definitely above or we're actually below that reference. And so we are going to define this mathematically. We're going to define the reference as a collection of three statements and a before, an on, and an after. The before and an after are verifiable. An object can be on the reference. We need to have the reference. So there has to be an on. There can't be no on. We can't just have the before and after. We need the on. If it's not before and it's not after, then it has to be on. So the case where we are, if we're not here, we're not here, we have to be here. And if it's before and if it's after, then it also has to be on, right? This is, and so we don't have all possible assignments for this table, right? The assignment false, false, false is not gonna be, it's not gonna happen. And also true, false, true, it's not gonna happen, right? So these are the basic requirements that we can have on statements, on references. The first thing that you need to be able to get to a linear order is that you need to remove the overlap. Otherwise, you're not going to get to a linear order. It becomes a lot more messy stuff. So you need to be able to say that the thing that you are measuring, it's always either completely before, completely after, or completely on, which basically means that the extent of the thing that you're measuring, right, it's very small compared to the size of the on, right? So your tick of the event that you're doing, it happens faster than the resolution of your prompt, for example, something like that. That's not enough to have a linear order, because you could have two references that are not aligned. Like for example, if you have this, if you are in space and this is a before the reference and after the reference, we have two references like this, we could have all the 9 combinations, and this would not make the things, the references align, and then it's not going to give you a linear order. So we have a definition of a line that has to be general enough, and it turns out is the way that you define the alignment is that you look at the before and the after, and the not after, sorry, the before of both references and the not after of the two references. So you say that these are aligned because if it's before the first one, then it has to be before the second one. And if it's before the second one, it's not after the first one. And if it's not after the first one, it's not after the second one. So you basically have this chain of implication between the references. And the insight is that this ordering, that this is going to be an ordering of, in the logical sense, it's an order in the implication, and implication actually creates a partial order. This order in the logic structure will become the order in the points, such that 1 is before 2 precisely because if we say that something is before 1, it's also going to be before 2. So this implication in the statements is what then is going to give us the structure of the ordering of the points, which I find absolutely beautiful and interesting. Now, that's not going to be enough to get to the linear ordering, because you might have overlap within the reference, and you need to be able to resolve those overlaps. And there are 2 types of overlaps that you can have that you need to be able to resolve. The first, an actual overlap where you need to basically distinguish whether you are on this part or on this part of the reference. And then the sort of the overlap of the open parts. You always need to be able to put something in between if there can be something in between. And this basically gives you a refinable reference system. You can always go and figure out if there is some empty space between 2 references, I can always put something. And if there is some overlap between 2 references, I can always also put there something to distinguish this. And with lots of pages of proofs, you can then show that to define an order sequence of distinguishable cases, so of this instance of places in space, in values for some different quantity, then these are necessarily a sufficient condition. The set of references have to be strict, they have to be aligned so that you get a shared notion of before and after, and they have to be refinable such that the overlaps can always be returned. And this gives you points with an order topology. This is the hard bit to get. Once you have that, knowing whether you have real numbers or integers is just whether you have a dense set of references. Where you have 2 references, you can always put something in between. If you can always put something in between, you have the integers, And if you can't put something in between, then sorry, if you can always put something in between, you can have the real numbers. If you cannot put something in between, you can only put infinitely many. Then you're gonna get an integer. And now what happens is now that we have clarified these conditions, you can say, okay, are these things that are tenable, for example, for something like space and time? Like, can we really say that these are things that we can keep, or they are idealization? And of course, they're going to be idealization. And so, for example, the fact that the references are strict, as I said, it means that the resolution of the reference system is a coarse comparing to the width of the elements that we are actually looking at. And so if the tick of the clock have an extent and the events have an extent, and these the extent of the events and the tick of the clock are comparable, right? Because at the end of the day, we are going to use events to create clocks. Then you can't say that the references are strict. So it has to fail if you can't make that approximation. Now, another problem is that clocks have jitter. So they do this. If references keep doing this, then the references are not aligned, because sometimes something is going to be before, sometimes it's going to be after. So you're not going to be able to say that every time that this is before this reference is going to be before the other reference. So the lack of perfect synchronization means that your references on repeated experiments and so on, they're not going to be aligned. You can't guarantee this logical structure. And then the other problem, of course, that you cannot make ticks as narrow as you want. And so that means that your references are not going to be refinable, because at some point you're going to have a finite, like not a finite width, but a minimum width that you can't resolve anymore, but you're still going to have overlap between these references. So you're not going to be able to resolve this overlap. And so the problem with this is that you're not going to be able to have a consistent notion of before and after. So remember, these three conditions are there to give you an ordering, not to give you the reals. So what happens is that if you have to give up those assumptions, it's not that you give up the reals, but you get the rationals or you get the integers. You have to give up the notion of ordering. So the failure that you should have, it seems that has to be a lot more catastrophic. So the way that sort of it fails, I don't know how we resolve it, of course, I just know how it fails, but this is the structure that you can imagine, right? You can say that this is before this, and that this is before this, and that this is before this, but you're not going to be able to say that this is actually before this, or that this is before this. Like you can imagine to take this and swap it with this, like swap it here, and the ordering will still be preserved, right? So you're not going to have this a linear order that it's going to save you and give you like some nice quality. And one of the things that it's interesting to me is that you basically, what we would want, it's something that does not have order at small scale, but it has order at large enough scale. So I'm not going to be able to say whether two events that are very close to each other are one before the other. But if they are very far from each other, I should be able to say, yeah, this one is before the other. And in the current mathematical tool have a hard division between topology and geometry. And which means that the way that you distinguish things, and because experimental verifiability means distinguishing things experimentally, it does not depend on the size, right? It's a separate thing. And here we're saying that it's exactly the opposite. The way that we can distinguish things has to depend on whether two things are far apart or close behind. So there has to be a link between the topology and the geometry. You're not going to be able to define the topology without knowing the geometry, and vice versa. And so if this is the case, and again, these seems to be very simple reasons that are sort of very simply grounded, then it would mean that we most likely would need new math. When again, I have no idea what this math would be, and right now I'm not working on this. But if, again, this is something that we were discussing yesterday, I do think if somebody wants to seriously look at what are the mathematical structure that you need to look at this problem closely, and they're very hard problems, because I don't think there is math that you can simply go look and, oh yeah, you're going to find the problem solved. So that's basically it. So the main takeaway is that the real numbers can be recovered from essentially an idealized metrological model, where you have references and you can establish before and after with these references. And the ordering of value comes essentially from the ordering that you already have in the logical structure given by this narrowness operation that you can think as implication. So 3 is less than 5 precisely because there are less than 3 items implies or is a narrower statement than there are less than 5 items. The hard part is the ordering, not the continuity. And the difference between the real and the integer, it's basically trivial. It's just the ability to find something always in between two references. And the interesting part is, if you remember that the Cantor requirement for ordering with the reals, that it has to be complete. And what's happening here is that it's the topology that is forcing this ordering to be complete by the way that it's being constructed. And the outcome of having found these set of assumptions for getting the reals is that the failure of idealization under the real numbers actually would lead to a structure much richer, much more complication than a real order. And again, it to me is a completely open problem of how that would be described. So again, this is why I think that finding, we were talking about before, what happens is the axioms that you have are not large enough. Doing these things, it actually make you bubble up all the problems and all of the assumptions that you have to take to do things, and therefore you're much better in position to understand whether the axioms that you have can actually be general or not. Okay, so now let's go back and talk about ensembles and ensemble spaces. We saw before that we were trying to characterize ensembles and mixture of ensembles. That's part of a bigger project to basically define states and processes. And for states and processes, we need an in. We need something else that tells us how do we characterize this. And what we found, essentially guided by the work on reverse physics, we found that ensembles are really the key. But then, of course, you have to physically justify why do you need ensembles. And so we have this principle of scientific reproducibility that tells us the scientific laws describe relationship that can always be experimentally reproduced. And the fact that you have to be able to reproduce them right now is not just a matter of just having one verifiable statement verified once sometimes. No, it's the fact that you have to create it experimentally over and over. And what this means is that the laws cannot be about specific measurement at specific time. They have to be about collection of preparations and collection of measurements. And therefore, the scientific laws are really relationship between ensembles. So when we write F equals MA, we're not just saying, I have these numbers. It says whenever I prepare F in particular ways, I'm going to have an A that is prepared in particular ways. And so the physical theory, any physical theory, must at least describe which ensembles are possible within the theory, because I'm going to have a preparation procedure, which is going to give you an initial ensemble. I'm going to have a physical process, which is going to give me a final ensemble. I'm going to have a measurement procedure that is going to give me statistical data, and statistical data is an ensemble of the possible outputs of the measurement procedure. So at the very least, a physical theory needs to give me an ensemble, and therefore we need to find what are the basic axioms, something that all spaces of ensembles need to guarantee. And just to have some concrete idea of an ensemble, if we have a classical discrete space, we are going to have a series of points and a probability distribution over the points. If we have a classical continuous system, we have a phase space, we have a symplectic manifold, and then we have the space of probability distributions over that manifold. And if you're in quantum space, you have a projective Hilbert space for the set of states. Then your ensembles are these density matrices, the positive semi-definite intermission with trace one. So these are basically our target things, and whenever we make an axiom on ensemble spaces, we want to be able to make sure that these are going to satisfy, and we want to be able to recover these cases in the specific for the different things. So the first axiom of that we have is the axiom of ensembles, that tells us the state of a sigma of a system is represented by an ensemble, which represents all possible preparation of equivalent systems prepared according to the same procedure. And the set of all possible ensembles for a particular system is an ensemble space. So we know what an ensemble space, and since it has to be verifiable experimentally, definable experimentally, we know that it's going to be a T0 second countable topological space. And what is going to be key for us is the topology is what is responsible for handling limits and infinite operations, and all the other operations that we have in the space are finite. And this is similar to what happens, for example, in topological vector spaces. The vector space has a finite structure, but the topology tells you how you get limits and out. We have what we said before, that if we have two elements A and B, if two ensembles A and B, we can make a mixture, and this P bar, it's this 1 minus P. So we have PA plus P1 minus PB, it's a convex combination, and geometrically you can always represent the convex combination between 2 points as a point that lives on the segment in between them. A linear combination of 2 points, if I have two vectors, if I had an origin here, right, that would be the vector A and that would be the vector B, would span the whole space. But if you have 2 points and in a convex space or in a vector space, the convex mixture, the statistical mixture, is going to give you a point in between. And again, only the finite mixtures are guaranteed, because once you know how to make 2, you can make n mixtures. But the topology tells us where do you have where will your limits converge. And again, we are trying to develop this theory as similar as possible as topological vector space, because topological vector space is well developed, and it's what one uses to generalize analysis and do all of those things. But there is no theory of topological convex space. And this is what we need to build. So this is exactly one example, like an exact example in which we don't have a mathematical structure that fits nicely, that is the mathematical structure that we would need if we started from physically meaningful starting point. So, and we're slowly building it. And of course, if we can engage some mathematicians to help us, would be even better. Then the third thing that we need to define in an ensemble space is an entropy. And the entropy here is not some abstract quantity, it's something that quantifies the variability of the preparation of the ensembles. So if we have a set, and this is an ensemble, the ensemble is going to be all these infinite collection of preparation. There are going to be a bunch of things, and B is another preparation, is going to be a bunch of things. And you can see intuitively that this is less varied than this. And this is a statistical property that it's important because you're going to be able to see more variation in the outcomes here than here. So it's something that we need to be able to keep track. And the entropy, turns out, it's the thing that is going to tell us how similar are the preparation within the ensemble. Now, as you see, this right now is just defined as a function that is that takes an element of the ensemble space and gives us a number, and then it's going to satisfy a bunch of property. The first one is going to be continuity, because again, the entropy of an ensemble is something that we can go out and measure, and therefore it has a physical consequence. So therefore it has to be an experimental relationship, and therefore it has to preserve the topology. So it has to be a continuous function. It needs to be strictly concave, meaning that if we have two ensembles, right, and we put them together, right, so we have ensemble A and ensemble B, and we put them together, the output, the variability after the mixture can only be cannot be less than the average variability of what we put in. So if we have the things that have certain variability and we do a mixture, We can't have now something that is better precise. It can only be something where the variability increases. And if it stays the same, then it means that we're actually mixing the same thing. And this is what justifies the strict concavity. Strict concavity increases, the average entropy increases through mixture, and the equality holds only if the two elements are the same. And so this is a very simple thing that we can justify by knowing that the entropy is describing the variability of the ensemble. Another thing that we can justify is that there is going to be an upper variability bound. So suppose that the maximum increase in variability is going to be when we're mixing two things that are completely different from each other, right? That no element of A, no instance of A could be thought as coming from an instance of B. So these are two completely different things, such that when we mix them, we're only going to mix things that are completely different from each other. And that's the case where the ensemble are going to give us the greatest possible increase in entropy. And at that point, the increase in entropy is fully determined by the mixing coefficient. If we're mixing coefficient 0, we're basically not doing anything. But if we have a mixing coefficient 1/2, we expect the things to be much greater. And so this is going to be the fact that we have an upper variability bound. We have the entropy of the final mixture, we have the average entropy of the initial, and then there is going to be an increase that is given by P. And if A and B satisfy this upper variability bound, then we define these things to be non-overlapping. Like it's the fact that they saturate the upper variability bound that tell us that they are maximally different. Or we also call them orthogonal, because the notion of orthogonality that we have both in classical mechanics and quantum mechanics in all the vector spaces that we really need is actually this notion. It comes out of the entropy. And so this is, again, something that can be fully justified by the fact that we know that there is a variability. And then the other thing that we have as an axiom is that if A is orthogonal to B, means that all the elements are different, and A is also orthogonal to C, meaning that, again, they don't have any elements that are similar, then A is also orthogonal for any mixture of B and C, because if the elements are different, they're going to be like, you can't create different elements when we're taking mixtures. And again, this makes the space what you would expect, where the orthogonality have these types of properties. Okay, so basically we have here now that the ensemble variability is what give us the entropy. And again, there is no standard theory of this type of entropic space that we're trying to define. And so this is part of sort of, let's say, of research in math, right? We need to find the theorems, what are the things that these axioms are going to give us, how much they're going to give us. Are they going to give us all the things that we need or just partial things? For now, we know that we can actually justify these axioms and we can go. I'm not even 100% sure whether all these axioms are independent. I think that part of this axiom is actually already inside the previous axiom. Maybe this axiom could be proven to be redundant. I don't know. That's part of the sort of the thing that people do in the foundation of math. When you have different axioms, figure out which one are independent, which one are equivalent. Now, we need to be able to do these type of things, right? And again, I'd be very happy to do this with other people, partly because it's more fun doing it with other people, but because they're gonna have different intuition and that. So the point is that these are necessary. Like we can say, okay, if we have an ensemble space now for any physical theory, even the ones that we haven't discovered yet, we know that at least we must be able to satisfy these axioms. And now the game is what it is that we can prove from these. And there are a lot of things that we already proved. Keep in mind that none of this is published in a paper yet. They're just results that they're putting in our book, simply because it touches so many things that have no established field that it's even unclear to me where would we publish. And I'd rather to sort of finish the full theory first so that we know where all the pieces are, And then we can choose what are the right names for things and how the theory puts together and so on. Otherwise, you basically would try to write a paper that then after 6 months, you basically are going to say, oh, I should have done it in a completely different way. So we're allowing us that space, but the results that I'm presenting here are basically results that are solved. So the first thing that you can do is that you can, this upper bound that we have on the entropy, you can actually derive that it's the Shannon entropy. So I have here a visual way of how the calculation, this is basically just a calculation. And again, you're doing this calculation in a general space, but this is basically how it works. The whole premise is that when you have a mixture of mixtures, you can do a full mixture first or break the mixtures into 2 steps. So if you have a uniform mixtures of n times m elements, then you can make it as a mixture of n elements of a uniform mixture of n elements, where the n elements are the uniform mixtures of the m elements. And so by breaking, by doing the full mixture first or dividing into 2 pieces, you're going to see that this part here has to be equal to this part here. And now you are going to see that this quantity depends only on n and m, and this only depends on n, and this only depends on m. And you have a sum here, and this is the entropy over the uniform distribution. So you're going to be able to say that the increasive entropy of a uniform distribution over n times m element is the sum of the entropy increase of an distribution of n elements of n elements. And so you have that the product becomes the sum, and that's exactly the property that the logarithm gives you, and that's what you're going to be able to say, that the increase of entropy over a uniform distribution is going to be some constant times the log of the elements over which we are doing the uniform distribution. Then you can say, okay, now I know how to do a uniform distribution. Suppose that I have a rational distributions, so that I have 2 15s, 5 15s, 3 15s, and 6 15s, right? Well, I can either do the mixtures over these rational elements. This shouldn't say uniform mixture. You should say rational elements. But anyway, you can again do first the mixture over. I know this is the uniform mixture. Oh, sorry, of all the things that decombined of all the single elements, and then you can group these so that you obtain the rational distribution. And so again, you're going to have an increase of entropy if you do this mixture all at once, or if you do it into 2 steps. And that's what's going to give you this condition. And then you can take these conditions and get basically find the minus k p log p. That's basically how it works. And again, it's in the draft of our book. You can go and see the details, which unfortunately we don't have time. It's very nice. But the point is that the proof does not know whether we're dealing with classical ensembles, quantum ensembles, ensembles of any theory yet discovered. Like, it works in general. And the proof is basically short. It's about 2 pages of this type of calculations. And yeah, so we didn't need to put in the the formula for the entropy is actually derived from the previous axiom, which I find very satisfying. But everything that you can define with this notion of entropy, we saw before that we could define the orthogonality. So 2 elements are orthogonal if they saturate the upper bound, if they maximally increase the entropy after a mixture. But on the convex structure, we can also define 2 elements to be separate, meaning that there is no common component. So you can't find a C such that A can be seen as a convex combination of C with something else, and B also a convex combination with B and something else, right? So in the classical case, for example, this means that they have disjoint support, because if I have an overlap, then you can find a probability distribution within the overlap that then you can sum with something else to get one, and something else will be other. Now, it turns out that in general, with the axiom that we have, orthogonality implies separateness. So if 2 things are maximally increase the entropy, then they can't have a distribution secretly that it's inside both of them. But the inverse is not true. The inverse is true, the converse is true, if you are in a classical space. In a classical space, if two things are separate, they are also orthogonal. But it is not true in quantum mechanics. For example, all pure states are going to be separate because they don't have components. The only component that a pure ensemble has is itself. It's not made of other things. Right? And so all the ensembles, all the pure states that you can have in a block ball, they're all separate from each other. But only orthogonal pure states are orthogonal to each other. So it is not true that if you're separate, you're orthogonal. And the point should be that since this is essentially this is a defining characteristic, a defining line between classical states, classical ensemble space, and everything else, it should be possible to derive all other quantum-like features from this difference. I don't know how to do it, but that's what the math tells you. And that's very interesting because this is a completely different way of looking at these spaces, but it's of classical mechanics and quantum mechanics, but you are now comparing them, through some set of axioms that now are the same for both of them, which makes this comparison a lot easier to do because now you're talking about things that are similar to each other. Okay, there will be lots of other things, but we have to move on. Vector space constraints from the entropy. So it seems that the existence of the entropy makes the convex space a lot special. So first of all, convex spaces do not in general have a unique inverse, only if they are cancellative. But the entropy bound force this mixing to be invertible, which is very interesting because it essentially rules out a lot of cases. And this is one of those cases where I thought that non-cancellative convex spaces, I got excited, oh, maybe there is new physics there. And then I realized, no, actually, there is no physics. And then you can go through the examples and convince yourself that yes, that there has to be the truth. So this is where the math also guides, the physics and the math combined guides your intuition. Another thing that then you can prove because the space is cancellative is that ensemble spaces have to embed into a vector space. It's going to be a convex subset of a vector space, and the vector space can span further. So you're going to introduce unphysical objects, but it's, again, a convenient space to work with. And the vectors are basically differences. So if you fix A as your origin, then the difference between A and B is going to become a vector. And you're going to have a point on the other side such that if you mix C and B with an equal amount, you're going to get A. Then it means that the vectors between C and A is going to be the difference from, is going to be the negation of the vector between B and A. So basically, you can define all these vector operations defined from mixing operations so that you, again, you can keep tight the connection between these two things. And again, this is one, since we had the question about category theory before, some of these results I actually got from somebody that was looking at the convex spaces by themselves and had this theorem that proved that if the convex spaces were cancellative, they embed in a vector space. The construction that he had to create the vector space was very essentially, let's say, abstract algebraic categorically, in the sense that you basically take that, you make some closure, and then you quotient out with something. And the problem with those constructions is that even talking to other mathematicians, you can't build an intuition of what those things are. And since in our cases, we have to understand the interaction with the topology of those things, we couldn't get a good enough intuition. So this is one of, again, the problem of having math that becomes very abstract and you can't make concrete ideas. And in this case, we are looking at sort of a concrete version of convex spaces because it has more structure. And so we need to sort of analyze more what these constructions are so that we can get a better understanding. So anyway, we're going to have vector spaces, which is important. And another thing that you can show is that, as I said, the ensemble space has to be a convex set of the vector space, and this is our ensemble space inside the vector space. But not only is convex, it has to be bounded in all directions. And the way that you can prove it, and again, I got this intuition that this would be the case only by playing around on the Desmos calculator online and fixing things. And so let's say that we have 3 points, this point, this point, and this point. These are the ensembles over a line. So this would be the ensembles over here. And on the vertical side, we have the entropy. So we can fix 3 points at 3 different positions with some entropy. And then we want to have a 4th point with some entropy. And since the entropy is strictly concave, then this point has to be below this blue line. And since you have a bound, an upper bound, then this point has to be above this purple line. And so then you see that the 2 lines intersect, and therefore you can't put a point past a certain point. So this is a geometrical intuition. And then once I figured out how to do this, then I wrote the math, and the math actually checks out. So again, multiple ways of looking at the problem always helps. So these are some properties that we can get in terms of vector spaces. What we also can find is, as we saw before, there was a connection between entropy and geometric structure. You can also find this in the entropy in these ensemble spaces. You can define a sort of something that looks like a distance. If you have 2 ensembles, you can say how much does the entropy increase if I mix those 2 ensembles by 50% each. If they're the same, right, the entropy does not increase, so that is 0. So, and it's 0 only if you're mixing the same thing. So you have a lower bound on 0 that is only there if the 2 things are the same. And if it's maximum when they are orthogonal, and if we're measuring things in bit, then this is going to be 1. So this is a quantity that is going to be between 0 and 1. And it's also symmetric. And so it kind of is like a distance. It tells you how far 2 states are apart, except that it does not satisfy the triangle inequality. And this is actually something that recovers what is called as the Jensen-Shannon divergence, which is something that is defined in information theory. And if you don't know what this is, you might have heard of the KL divergence. This is a symmetrization of the KL divergence. But the point is that this quantity that is abstract, defined abstractly on the ensemble space, reduces to both the Jensen-Shannon divergence in both classical mechanics and quantum mechanics. When you have that, you can now define a notion of distance on infinitesimal change, on variation. And then what you find is that the strict concatenative means that the Hessian of the entropy is negative defined. So if you put a minus sign, which is what you find when you make this calculation, you find that you have a metric tensor-like thing on the space of ensembles, which actually recover the Fisher-Rao information metric for both classical mechanics and quantum mechanics. So again, with very simple calculation, the calculation is sort of trivial, but we don't have time to go through it. But it's something that fits in a page, and again, it's completely general. It doesn't care what the underlying space is, and it tells you that this thing always exists for any ensemble space. So again, if you want to create a new theory of quantum gravity, whatever, this is going to be there in some shape or form. And everything that we want to recover, not just geometric structure, but also measure theoretic structure, your probability measure, your count of states. So those are everything that we want to get. So in classical mechanics, you have the connection between the entropy uniform distribution and the logarithm of the count of states. And so can we do something like that for ensemble spaces in general? And it turns out that you can. Because the exponential of the entropy, right now we're going to start with the entropy and not with the count of states, right? So we're going to have to do the exponential of the entropy, which we also saw yesterday. It seems to be a quantity that recurs. The exponential of the entropy has a very nice property that it's subadditive. If you have 2 ensembles and you mix them, then the exponential of the entropy of the mixture is less or equal to the sum. And it's the sum only if you're combining ensembles that are orthogonal, which, for example, in the classical case would mean disjoint support. In the quantum case would be orthogonal subspaces. And if you're mixing them in the correct proportion, so that you're giving a higher weight to the one that is bigger in some sense. And so again, these properties are things that you can prove in general. Simple calculation on any type of space, which means so these are truly general things. And then what you can then do is define what we call a state capacity, and we call it state capacity because capacity is another name for a non-additive measure. So given a set of ensembles, we want to say how much is the spread of those ensembles in terms of the pure states that you could put in on the physically defined cases. So you take that subset of the ensembles, you take the space of all the possible mixtures, you get the highest entropy, because the ensemble with the highest entropy is going to be the uniform distribution. So you're basically saying, I have a subspace, I take the element with the highest entropy with the uniform distribution, and then I take the exponential of it. And then once I take the exponential of it, I call that the count of states. And in classical mechanics, it recovers the usual count of states, it recovers the Liouville measure. And if you're using subspaces in quantum mechanics, then it recovers the dimensionality of the space, which is the count of distinguishable space. So again, this is something that we can define very simply in general and recovers things that are interesting. And the only quirk is that this is a non-additive measure, meaning that if you have two sets that are disjoint and you do the measure on the union of both, you not necessarily get the sum of them. You're going to get something that is actually lower. It's going to be subadditive. Similarly, we have a notion of probability that does not talk about outcomes of measurement, but it's defined in terms of how do we mix things. So this is the thing that it's different in classical mechanics and any other space. And in classical mechanics, you can mixing things, so creating an ensemble or taking probability of outcomes is the same thing. So these coefficients that you use in the mixture are the same coefficient that you use when you get out a probability out of it. In quantum mechanics and any other space, it's not necessarily the case. And this is what is different. And so since we can't get a notion of probability that works both in classical mechanics and quantum mechanics on the probability of outcomes, what if we have a similar notion of mixture in classical mechanics and quantum mechanics such that it becomes the same? And it turns out that you can do, given a set of ensemble, you can ask, what is the biggest P that I can put in front of a convex combination of those such that I get my E? So if you have an ensemble, how much of this ensemble can I think as made of mixtures of all these other preparations? And you can define this. It's going to give you, again, another measure, but then again, it's not going to be an additive measure. It's not going to be a subadditive measure, but again, it's something that you can define and study in general. So what is the point of all this? Well, we can, the argument here is that if we allow for the principle of scientific reproducibility, then that requires notion of ensembles, because we must be able to prepare repeatedly both preparations and measurements, and then the relationship of a physical law is going to be in terms of those ensembles. We can develop a theory of states and processes using ensembles, and we have right now a few physically justified starting points, but they still lead to a rich structure that recovers a bunch of things that we already have in classical mechanics and quantum mechanics, but we can do it over a general structure. And these notions, the thing that is mostly interesting to me, prepare a core foundation that can link various standard mathematical tools. What I mentioned yesterday, that one of the things that I realized while doing reverse physics is that all these different characterization use different mathematical tools, and you always have to translate one to the other. The idea is there should be a core physical theory that connects to all these different ways of looking at it. And I think that's what we're starting to see. Topological vector spaces are the foundation of modern functional analysis, and we can see that we do have a topology, and the convex space becomes a vector space. We need to understand how to get to see how we get the topological vector space. Information geometry can be shown to link to symplectic geometry of classical mechanics and the inner part of quantum mechanics. So it's very likely the geometrical structure that we're having, if projected in the right way on the space of idealized states, then we're going to be able to recover those structures. And non-additive measure provide a generalization of classical measures of theoretical structures. And again, maybe there is a generalization of integration and differentiation that will make sense as that. And since there is a lot of work to needs to be done to the theory, but the point is that there are also a lot of nice results that once are found, they become very simple. So to wrap it up, physical mathematics, again, the goal is to derive the math from physical requirements. We have this notion of scientific objectivity with evidence-based assertions to get the notion of sigma algebra and topological and topologies, and real numbers can be understood as a modeling of idealized reference system. And we have ensembles from reproducibility. And again, so hopefully this gives you a sense that we can sort of do something that really goes in the nuts and bolts of the math while actually still keeping a sense of what these things are physically, and quite frankly, find also a lot of new and interesting math. So even for mathematicians, I think that this would be interesting. And that's it.
Right. Let me see. Xinwei is still connected, and I had actually forgotten about a question they had asked previously during the other lecture. So currently, it seems that there are way too many pieces of maths in the physics field to be made sense of.
What is the question?
Well, there's a question mark. So are there currently way too many pieces of math in physics to be made sense of within physics?
So let's put it like this. There is always an increasing number of math things because there are a lot of mathematicians that try to take things and create new things and so on. For example, just a couple of weeks ago, somebody contacted me because they're working on continuous logic. And they're working on a way to reframe quantum mechanics in terms of continuous logic, which I didn't know it existed, before he talked to me. There is a sense that a lot of the things that we need to do in physics are the things that we need to do in physics. So at some level, the mathematical structure that we need sort of in some ideal world are going to be those, and then those can be implemented in many different ways, right? So there are going to be multiple ways to define the mathematical structure that are going to be sort of equivalent to each other. So yes, there are people that do a lot of things, and not all of them are going to fit exactly the math that we need. My approach is to use come si dice? As much as we can, the mathematical structure that are the most common. So, for example, I'd rather use a set theoretic structure than a categorical structure, because the majority of the mathematicians that I'll talk to are going to be a lot more comfortable with those things. So even though the same structure can be described in a set theoretical way or in a categorical way, I'll go with the one that increases the chance that I get the collaborators. In the same way, when I recover topologies, I want to recover topologies with terminology that everybody in math knows and uses, because the biggest problem is, again, creating a community that helps me analyze the thing in all that. And then, as always happen in academia, there is going to be too many things so that you can to be able to be aware of what everybody's doing. But fortunately, you don't need to be aware of everything that is there to be able to make progress.
Okay, Chinwe has clarified in the chat that was supposed to be a comment on the Clifford algebra question asked previously.
Right, so Clifford algebra, I looked at specifically because there were some results and I thought, oh, this might be nice. And so I sort of at least got a sense of what they are and how they work. But then I decided with the limited time that I spent looking at Clifford algebra, that I would be better off working with topological differential topology and sort of variational calculus, because those structures are going to be closer to the things that we need, right? And so those are the type of valuation that we basically do, and of course they're not always going to be correct, and sometimes you say, oh, actually, I should have used that, but.
A question from the chat from Shad Azmi. An integer-based reference system solves Zeno's problem?
So Zeno's problem is already solved by essentially, I can say, by calculus, in the sense that that's basically just a problem of making the limit. So what Zeno is doing is sort of like he's dividing things, but it's not making ratio of things. So it's dividing, let's say, the space, but not also dividing the time, and therefore that's how he gets the paradoxes.
Going to the Q&A, a question from Daryl. Can you elaborate on how completeness is implied by the topology? I remember completeness is not a topological property.
Correct. But if you have something that looks like an ordered topology, and so there are two things. So imagine that we have these references, right? And I can define these before and after. And now imagine that we have the references that are, all the references, let's say, that are, that tell you, how can I say? Okay. Let's do two things. The union of open sets is an open set. So if I take something is before, let's see, I have to make this correct. Something is before 3. Something is before 3.1. Something is before 3.14, and so on. I make the union of all of that. I'm going to have something is before pi. So in that sense, the topology allows essentially to make these sets, right, of something, let's say, is before a rational. Then what happens, if you remember, we had to find references such that I have a before, I have an after, but I always need to be able to put something in between, right? So a reference cannot have just a before and just an after with nothing in between. So if your order would not be complete, right, say that I'm getting the rational, I would be able to have something that I basically can be able to test the value is before pi. I'd be able to test that the value is after pi, but I wouldn't have that on pi. So I wouldn't be able to construct a reference. So with the fact that I'm describing references, the fact that I can make these unions, when I have a bunch of references, I can construct other references. And when I construct other references, I'm always going to be able to put something between the before and after. That something that is the before and after, it's the supremum for the things before, and it's the infimum for the things after. And that's how it makes magically ordering complete. So it's not just the topology, it's topology combined with all this notion of reference.
A question from Tobias. Regarding the axiom of entropy, it's plausible that we always have a notion of variability, but that we measure it with a real number, etc., is less intuitive. Is there justification in simpler terms? It looks like what we need is to distinguish elements and quantify their frequency in the ensemble or something like that.
So that's something that while writing the justification, I realized that I do not have a strong justification as to why the entropy has to be a real valued quantity. Assuming the entropy, the fact that you assume that the entropy is a linear, a real value quantity, is because you're assuming that you can always take two ensembles and compare them by variability, and you are basically going to have a linear order between these equivalence classes of variability. So something is either more variable or less variable or equally variable. It can't. You cannot. You can always make the comparison. So if you have two ensembles, they have a variability, you can always say whether, you can always compare the variability. Either one is more variable than the other, or the opposite, or they're the same. And I currently do not have a justification for why that would be the case. I do think that it should still be the case, because I doubt you'd be able to define, let's say, deterministic processes between two things, because deterministic and reversible processes are going to be stuff defined at equal entropy. Like there are all these notions that come out from maps, right? If I have maps from one ensemble to an ensemble and process from one ensemble to the ensembles, if there is no or like if you can't compare the variability, I think there are going to be a lot of other things that you can't define, and that it would not make sense. I do not have all of these intuition nailed down in a nice justification. So right now, the justification says that there is this hole, and that we are basically assuming it. And that's exactly the nice role of the justification, because they allow you to notice that you were making this assumption, and then you can decide whether it's you still want to keep it or not.
Related comment from Luther in the chat. Entropy is a signed measure on R, so R is a very natural place for it.
Okay.
Currently, no more questions in the Q&A or the chat, but maybe I can raise something. So for variability of, people have talked about applying information theoretic ideas to pieces of writing. You can look at variability in terms of, say, letters or words. People have done this for Shakespeare, for example. So for physical systems, how is it defined what the elements are that you're examining the variability of?
So this is where we are doing the opposite. We define the ensembles, and then the elements are going to be defined based on the ensemble and the variability. So the basic idea should be that even when we define, this variability could even be how much let's say a macro state is jiggling around with, or the state is jiggling around within a delta t, which is the time scale that they're using to define that state. And so I cannot talk. So it's a little bit like the tests. The elements that are of the variability are the single instances of the experimental of the output of the experimental procedure, and the physical theory only knows and talk about the collection of those, because it's on those that you're making the statements. You are going to be able to define sort of the elements upon which you can define ensembles in the standard way, only if you're able to prepare those instances consistently and make an ensemble out of them. So I can talk about, I don't know, having an ensemble of, characterizing the ensembles based on the fraction of two different molecules, for example. Precisely because I can create ensemble of the same molecules, and so I know, and I can always produce this molecule. I know what it is. I can always measure it in the same way, and so on, because basically you're making an ensemble that 100% you are preparing that molecule or the other molecule, and then you can think, okay, now my mixture is a mixture of these two ensembles where I always prepared one molecule or the other. In the case where you would not be able to do that, because all the things that you're producing are always things that jiggle around, and they don't always have all properties always well defined, that's where you're getting closer to the quantum pure state. Like, you have reduced the variability of some feature, and you're characterizing the state by those variables of things where you reduce variability, but you still have variability on other things. So I characterize my spin up and my spin down state, and that's all that I can characterize. And of course, there is still variability, because if I perform processes and measurement on other things, I see that there is variability because I don't always get the same thing, right? But then I characterize my pure state based only on some elements, even though even in that pure state, not everything is well specified. Does that make sense?
I think so. Or the ensembles are abstractions, right?
Yeah, some
very purposefully abstractions, of course, for the purpose of generalized ensemble spaces.
Like this is another thing where, you know, we are mixing ensembles with real numbers, and again, those real numbers are also idealization, and it's okay to have this idealization because the ensemble is an infinite set. So when I'm thinking about an infinite set, of course, I'm going to use a real number because that's going to be a limit process anyway. So this is where it's basically the problem that we were talking about the last time. Can you even create a physical theory where you are not, where you don't have some idealization somewhere? And if we're saying that, so we're saying right now that states at least need to be able to be described through ensembles. If we're able to show that that's the only thing that we can do, and the ensemble is an idealization because there is no such thing as infinite collection of things, that's where you're going to be able to say, oh, okay, then of course these are only models, and is only going to be about this fictitious of things that are sort of idealization of the things that we actually do.
Sure, you're always going to have some kind of idealization somewhere in the system, or somewhere in your framework.
Framework, yeah.
Yep. Let's see other questions.
So if there are no other questions on this particular topic, you can also ask a question about anything of the project, or we can just close it and call it a day. You guys decide. Oh, I didn't see the comment. Yes, it's the order topology that allows you to define the completeness more than just a concept of topology itself. Yeah.
Do you want to make any comment on how this entropy can connect eventually to thermodynamic entropy?
Oh, I'd rather do it tomorrow when we are gonna talk about
yeah, sure. It'll be in the yeah, part of the open problems that have some ideas already.
I'd say we just close if there are no questions.
That is fine on my side.
Okay, so I thank everybody for for sticking it out for this second day, and I'll see you guys tomorrow if you're here.
Thank you.
Bye. Okay, this time the stream